Hello everyone, in this video we are going to talk about pushdown automata. We have talked about regular languages and we have seen the type of machine that accept regular languages. Those type of machines are called finite automata, deterministic finite automata, non-deterministic finite automata, epsilon non-deterministic finite automata. All of them are representing the same power of the machine. So for the context-free languages, of course, the finite automata is not going to be enough. We are going to talk about the machines, the type of machines that can accept context-free languages. We give it a language, a string, and it actually accepts it or rejects it. It basically represents that if the string is in this context-free language or not. This kind of machines are called pushdown automaton. Why we call it pushdown automaton? Basically, the reason is, finite automata was not enough to accept context-free languages, because in finite automata, we only have finite number of states, right? So that power, that limited amount of space, memory, is not enough to accept context-free languages. So we are going to, give more power to our machine by adding a stack. And that stack, basically, in theory, you would assume that the stack has infinite amount of memory. It has access to infinite amount of memory, so it doesn't matter how long the string is or how much information you are going to store in the stack. So it makes it more powerful than a regular, just a finite automaton, right? So just assume that our machine not only has a finite number of states, but also it has access to a stack. That's why we call this type of machines pushdown automaton. So basically, because it has access to a stack and it pushed some information into the stack whenever it needs it. So you can see that this machine is still not, doesn't have enough power, just like the regular computers that we have, because we have all of the previous restrictions over reading the data. You get the data over some kind of tape, and you read it from left to right, and you would never actually you are not able to read the string again. If you have read a token, you are not going to actually go back and read it again. So this type of machines are still going to have less amount of power than the regular computers that we call them Turing machines. At the end of the course, we are going to briefly talk about the Turing machine as well. So let's see how the pushdown automata is going to work and how using the stack is going to help us to accept context-free languages. Remember this language, this was the very first language that we have seen. It is not a regular language. N number of zeros followed by exactly n number of ones. This is not a regular language, but we know that this is going to be a context-free language, and I'm going to just show you that how the stack is going to be adding a stack to our finite automata is going to help us to accept this language. If the number of zeros, n, is limited by a constant value like k, doesn't matter how big is k, million, milliard, whatever, the biggest number that you can actually think, but it is going to be a constant number, it is going to create a regular language. You can create a finite state machine. Although the number of states might be very large, you can create a finite state machine for that, because that number is fixed. You cannot get anything bigger than that, right? So for example, if I set k equal to 3, this is a small, I'm going to just give you an idea that if, for example, k is going to be equal to 3, using 2 power 3 number of states, you can accept this language, all right? The language that has only this number of strings. 2 power k number of states is going to be enough. So if k is fixed, you can create a finite state machine for that. But when k is variable and you don't know how long the k is going to be, how big the k is going to be, it's not possible to create a finite state machine for that. So I'm going to empower the machine, the finite state machine, by adding a stack you can see that the stack has infinite amount of memory. You can store any amount of memory to your stack. That makes it more powerful than finite amount of states, finite number of states. So for this language, I'm going to create a pushdown automata with a finite number of states. A pushdown automata is basically a finite state that has access to a stack. So a finite number of states and a stack. Let me give you some example. This is going to be my finite state in my pushdown automata. So you can see that the notation is a little bit different than what we have seen for the regular finite state machines, for the regular languages. The transitions here are a little bit different. How we read the transition, for example, this transition tells me that if you see token 1 in the input string, and if the token on top of the stack is x, then you can go to the state q1. From q0, you go to q1 if the input token is is 1, input is 1, and the top of the stack you can see that when we are saying we have access to a stack, it has all of the constraint of the stack. If you have a stack, you cannot read the whole content of the stack. You can only have access to the whatever is the top of the stack. So this is one other restriction over the this memory. Although the memory is infinite, you can only actually push to the top of the stack or pop from the top of the stack. So what is, this note, whatever I have written here basically tells me that we just pop from the stack. Regularly, there are different notations in different textbooks. If you search online for the pushdown automata, you will see that there are plenty of different notations, although unlike the finite state machines that the notation was unique. For the pushdown automata, the notations are a little bit different. For example, we use backslash here between these two parts of the transition. That basically this part tells me that what is the state of the input and what is on top of the stack, and this part tells me that what action I am applying over the stack. If you just see a couple of actual different notation, you will get used to it. Then I'm just trying to tell you that the notations are is not unique, and you will see different type of notations for the pushdown automata. So for example, I have seen a lot of this type of notation that, for example, you instead of writing it using a backslash, you write it using a arrow, something like this. Okay, this part, this action, what does this mean? It means that you just pop whatever is that value which was on top of the stack, you will pop it from the stack. So this is the action that we apply over the stack. So let me show you the formal definition of the pushdown automata first, then we will come back to this pushdown automata and see that how it works, apply it over a couple of examples. So we will show a pushdown automata using a 7 tuple. The first one in the tuple is basically the number of states. This is something, the number of states in your finite state. You see that the pushdown automata consists of a finite state and a stack. Okay, so Q is just like what we had in a finite state. Sigma is the alphabet, all of the tokens, all of the symbols that we have in our input string. And we also have this notation that G, I think, yeah, we call it G. And it is going to be, you know, the alphabet for the stack. This is going to be the tokens that you push to the stack. In all of the examples that I am going to show you, I'm going to use different tokens than the different symbols than the alphabet symbol, just to make it clear. But you can use the same set of symbols for the for pushing to the stack as just the sigma, the alphabet of the input string. There is no restriction over that. I'm just trying to use a different set of symbols to make sure that it is clear what's happening in the stack and what is the input string. We are going to have a starting state, just like what we have in a finite state, Q0. And we are going to have a symbol that is the initial symbol in the stack. So at the beginning, the stack is not empty. We only have it. You can actually think about it in this way, that at the beginning, we always have a symbol in the stack that this symbol is unique. You would never use it. I mean, you shouldn't basically use it later. It's going to tell you that you have reached to the end of the stack. It's a kind of, you know, indicator that the stack is empty. I mean, so we call it Z0, and or maybe you actually call it something else. But anyway, this symbol is going to be unique. That shows that the stack is empty. I mean, basically it shows that it is the starting state, just like the beginning state, the beginning situation. So what else? Yeah, we have a set of final states, just like what we had in a finite state machines. And we have also some, you know, a function, a transition function. How the transition function works, you would actually, in each state, in each situation, you are going to be in one of the states, right? One of the states from your finite state. You will read some symbol from the string, or you can actually have, you know, read the epsilon, which means that you are not reading anything from the input symbol, but you just do some transitions. So that's why we are going to use the sigma, the input alphabet, and also the epsilon, which means that you are not reading any token from the input, but you do some action transition. And the last part is the what is the top of the stack? So one of the symbols from the stack alphabet. So whatever is the top of the stack, based on that, it actually gives me a situation, which state you are in, what token you are reading from the input, and what is the top of the stack. So you will see that the first two parts, we have seen these two parts for the finite state, but we are going to add, you know, a symbol from the top of the stack as well to our transition. And from this situation, you go to, you know, another state, right? And you do an action over the stack. You basically, I mean, the notation is that we usually actually, whatever is the top of the stack, you pop it, and then if you wanted to actually keep it in the stack, you have to push it back. And for example, you can push more than one token to the stack at each position. So that's why I'm actually representing it as a L star. It means that you can, for example, in one action, in one transition, you can push more than one token to the top of the stack. And basically, whatever number of tokens that you want, you can push to the stack. In each action, we will just pop one token from the top of the stack, but you can push as many number of tokens as you want to the stack. We will see some example and it will be more clear. So let's go back to our previous example. So each of the transition that we have, here you can actually see a better, in more details that each transition, what does each transition mean? We are going to represent each transition in two parts. That this is going to tell me what is the input that I'm reading from the input string, what is the next input symbol, and what is the top of the stack, and y is going to actually tell me that you move from the state qi to qj, and y is going to be the set of symbols that you push to the top of the stack. So y can be represented using, y can be, a string of any length from the from G, right? So we represent as a G star. So if you actually write it as an epsilon, you will see that here I clearly just write pop, but I think in your textbook as well and in many other sources, instead of pop, it actually just represented as epsilon, which means that we just pop the token from the stack and we don't push anything to the stack. So if you, in the transition, instead of pop, I wrote epsilon. If you see epsilon, it just basically means that you just pop something from the stack. You pop Z0 from the stack and you didn't push anything, right? So epsilon means that you didn't push anything. If y is x, it basically, for example, whatever it was x, if you just write x here, it means that whatever I popped, I push it back to the stack. Basically means that I didn't change the situation of the stack. But by convention, we always actually think that whatever is the top of the stack, we pop it. If you want it back to the stack, you should push it. So basically, if y is equal to x, it means that you pop the x, but then you push it as well. Push it back. So if z is a string, any string longer than one token, whatever is actually the number of those tokens, it's just like you pop x, then you push these strings in the reverse order. So whatever I wrote as y, so zk is going to be pushed first, then zk minus 1, then to the beginning. So basically whatever is this string, if I write it, look at this, something like this, it actually tells me that I will push z0 first, then I will push x. So basically the stack would look like this, z0 and x. It just tells me that the top of the stack is going to be on the left. Okay, so this symbols has been pushed to the stack in a right to left order. So in this action, you first push z0, then you push x. Here is just actually give you the, what does this transition, for example, means. It means that if you are at Q0 and you see a 0 in the input string and the top of the stack was x, push that x to the stack and push another x as well. Basically, it means that whenever you see a 0, just push, and the top of the stack is x, push another x to the top of that. this transition tells me that if you are at Q0 and you see a 0 in the input string, just keep that Z0 and push another X to that. So in total, this two transition tells me that my action is whenever I see a 0, for each 0, I push an X to the stack. It actually makes sense, right? It's going to count the number of X in the stack will actually keep track of how many zeros I have seen. So later on, when I am actually going to start seeing the ones, for each one, I will pop one X from the stack. Okay, so this transition actually tells me that whenever I started seeing ones, you are at Q0, and whenever you see a 1, it means that, okay, you are done with reading this part, and you started reading this part. And we wanted to make sure that the number of ones are equal to the number of zeros, right? So I have kept, for k number of zeros in the stack, for each k number of X to the stack. So for each one that I will see, I will remove one of those X's from the stack. So in this way, kind of I can count the number of zeros that I have seen, right? So for the very first X the very first one that you have seen, the top of the stack should be X, right? Because if you see a 1, it means that there should be some 0. You should have already pushed some X to the top of the stack. So you pop it from the stack, you read 1, 1, and you pop 1X. And then you move to this state. So basically, a state Q1 is going to represent that state that, okay, I have read all of the zeros and I have seen the first one, and then I'm going to count all of the ones here. For each one that I'm seeing, if the top of the stack is X, just pop it. Okay, and you will continue until you reach to the end of the string and you reach to this situation that, okay, the top of the stack is Z0. It means that you have read all of the, you have matched all of the zeros. You have removed all of the X's from the stack. There is nothing else in the stack except the original Z0, which was on top of the in the stack. So this is going to basically tells you that you have reached to the bottom of the stack, and you remove it and you go to the Q2, and you can see that Q2 is a accepting state, right? And it basically tells you that, okay, whenever you by epsilon you will move, it means that if there is any more token in the input string, you can actually move to Q2, but because you haven't finished the input string and there is no transition over Q2, you will reject those strings if there is anything more. So this pushdown automata can be written in a form of a set of transition, this delta function, and it's actually showing me all the transitions that I have. Right, I only have 5 transitions here, and I'm representing all of that using this table. You can either represent it using, in this way, using a, the state diagram, or you can represent it using a table. So let's just, run this pushdown automata over some input string. It makes it more clear that what's happening. So just assume that I have an input string like this. This is in the language, right? So we wanted to see that how the machine is going to accept this string. At the very beginning, I haven't read anything from the input string, so it's just like the reading head of the machine is at the beginning. I haven't read anything, and the top of the situation of the stack is like this. You can see that there is nothing in the stack except Z0 that represent the stack is empty. The only token in the stack is Z0. And we are at a state Q0 as well. By reading the first token, 0, you will see that at Q0, the only transition that I have over the seeing 1, 0 is that, I mean, there are two transitions, but depending on what is the top of the stack, it tells me that, okay, I read 0 and the top of the stack was Z0, right? What is the action? Push back that Z0 to the stack. So it's just like, don't touch it. You popped it, right? And push it back to the stack and push 1x to the stack. So after reading the first token, we are going to still stay at Q0, and the situation of the stack has been changed. The top of the stack now is x. Basically, I have seen just 1, 0, and I only have a 1x in the stack. We read the next token. The next token is also 0. The corresponding transition is going to be this one. Why? Because the top of the previous top of the stack was x. You were at a state Q0 and you see a 0. So this is going to be the transition, which means that, okay, push back that the original x. So I haven't actually touched that. So I popped it and then push it back. And then push another x as well. So now I have seen 2 zeros. I have 2 x's, exactly the same number of zeros in the stack, and I'm still at a state Q0. Next, I am going to see a 1. So by seeing a 1, you see that the transition at Q0 by visiting a 1 and having x on top of the stack was to just pop that token, that x from the top of the stack, right? So the previous situation was that I had 2 x's. Now I have seen 1, 1. I am moving from Q0 to Q1 and I'm popping that x from the stack. So I only have 1 x in the stack remaining. The top of the stack is 1. Then I will see another 1. So the transition here is that if you are at Q1, you see a 1 and the top of the stack is x, just pop it and stay at Q1. So by reading the second one, the situation of the stack is that I actually reached to Z0. No other token is in the stack, and I'm still at Q1. So at this situation, I'm done with the reading the input string. There is no more token to read. The only transition, possible transition in the machine is that it's telling me that if the using an epsilon transition, I shouldn't actually call it epsilon transition because it's not like the finite state. It's just telling me that by not reading anything from the input and the top of, if the top of the stack is Z0, you can pop it and go to the final state Q2. And it means that we have accept the string. So basically in the pushdown automata, there are two different situations that we accept the string. I'm going to talk about it later, but for now, just take it from me in this way that you should completely read the input string. You should be at the end of the input string, nothing remains to read, and you are at a final state. So this is going to, in that way, you are going to accept your string. This part is going to be similar to what is going to happen in finite state machines, right? You should read the input strings completely, and then you should be in a final state. Only in that case you accept it in the finite state. In the pushdown automata, there is another case that we will accept the string that I'm going to talk about it later. But for this type of pushdown automata, we read the full input string and we were at a accepting state. So that's it, we accept this string. So logically, if we want to think about this pushdown automata, the idea is very simple. I want to read all of the zeros and I want to keep track of how many zeros I have. I cannot keep track of them using the number, the states. The number of states is going to be finite, but I have access to a stack, right? So for all the zeros, for each zero that I read, I will push 1x to the stack. So this part, the first phase is that, okay, for all the zeros that you read, just keep them in the stack, count a zero and keep it to the stack. And you see that all of these zeros should be sequential. As far as you are at Q0 and you see a 0, then you will actually keep and grow the stack. You just store x's into the stack. Whenever you started seeing a 1, you have to move. The transition tells you that you should move to Q1. And in the state Q1, we just count the number of ones. And the number of ones should be exactly equal to the number of zeros. Why? Because the only possible transition to an accepting state is that you have reached to the empty stack. It means that all of the ones, all of the x's that you have pushed to the stack should be removed. The number of zeros should be equal to the number of one. There is no other way to reach to the accepting state. And after that, if there is more ones, if there is still some one in the input string, you are going to reject it because there is no valid transition over Q2. If you haven't read the input string completely and you reach to Q2, this is exactly what would happen in a finite state machine. If there is no transition, your machine will stop and will reject the input string. So let's try it over some examples which are not in the language. That actually helps you to understand that what would happen if the string is not in the language. Something like, for example, 001. So let me actually show it to you here. I'm going to represent the situation here. You have the stack. The top of the stack is Z0. This doesn't really look good. Let me just draw it again. Okay, and you are going, this is the situation of the stack, and you are going to be at Q0, and the input string is 001. I read the first 0. What would happen? The transition tells me that if the top of the stack is Z0 and you see a 0, you push 1x, you push Z0 back to the stack and you push basically 1x to the top of the stack, okay? And you stay at Q0. Then I will read the next 0. With the next 0, this is the transition, right? You will push another x to the stack and you will stay at Q0. Then I will see a 1. What would happen over this transition, if the top of the stack is x and you see a 1, you would just pop that stack from the that x from the stack and you go to a state Q1. So what would happen is that I'm going to be at a state Q1 and 1x will be actually removed from the top of the stack. So I am at Q1, I am at the end of the string, right? There is nothing more to read. I am at Q1 and the top of the stack is x. Is there any transition for me? You see that if you are at Q1, there is nothing to read, right? You can actually use only epsilon the input token epsilon, and the top of the stack should be x, but there is no transition for this situation, right? So the machine is going to reject this string, and this string is not in the language, right? So let's see the other example, that you are going to have a string like 0, 0, 1, 1, 1. You will be at Q0 at the beginning, and the top of the stack is Z0. So you will read the first token using this transition, using the transition here. You will keep Z0 in the stack, and you will push another 1x to the stack, and you will stay at Q0. By reading the next 0, you will push another x to the stack, and you will stay at Q0 using this transition. By reading 1, 1, you will move to Q1. The top of the stack is x. You will move to Q1, right? And you pop that x from the stack. You read another token, which is 1. This transition tells me to pop the x from the top of the stack and stay at Q1. So what would happen is x will be removed. Let me actually just remove all of these arrows, and I am done with this part, right? And you are still at Q1. So there is one more 1 in your input. You have to read this one, right? The last token. And the top of a stack is Z0, and you are at Q1. Is there any transition at Q1 with this situation that the top of the stack is Z0 and you see 1 at Q1? There is no transition. Again, the machine is going to reject this string, and you will see that the string is not in the language. The number of zeros is not equal to the number of ones. So now to actually understand, to give a more formal notation to represent the actions over the pushdown automata, I'm going to define this term instantaneous description, that we will use it as ID for pushdown automata. Basically, it actually shows me that each situation of a pushdown automata is going to be represented as a configuration, right? That configuration will be what remains from the input string to be read, which is W, which state I am in, what remains from the input strings to read, and what is the content of the stack. And basically we represent this content, if you, for example, if you have the content of the stack is something like xz0, we will represent it as, so y will be xz0. So you will read it from the left to right, which actually means that from the top to bottom, what is the content of the stack. This tells me each situation that the pushdown automata can be in, each configuration, a configuration in each situation of the pushdown automata. So let me actually show you a couple of examples. Now I'm going to actually define the other symbol, the other term, trans-style notation, which basically tells me that, this is the sign for that. I don't know if there is a name for it or not, but anyway, this trans-style notation tells me that if you are at this situation in your pushdown automata, which means that you are at Q0, the stack, the situation of the stack, the content of the stack is just Z0, and your input string, this is the what has been remained from the input string that you are going to read. For example, if you are at the beginning, this is going to be the full string, right? You are at Q0. This is exactly this, something that I'm actually representing here is exactly what we were informally actually discussed here. These notations are going to just help me to represent that situation, you know, just mathematically how to have a written format for it. So this is going to tell me that you are at Q0. The string that remains to read is 001, and the content of the stack is only Z0. So this transstyle notation tells me that one action, I mean the one possible move here is that from this configuration you can move to this configuration, which based on this Pushdown Automata, it tells me that okay, you have one transition, one move, which is possible, that the content of the stack will be xz0, which means that the top of the stack is x, you push one x and you read one of the zeros from the input string, so the remaining is going to be 0, 1, 1, and you are still at the state Q0. This is going to be another, for example, transition that, for example, you are at Q0 and the remaining string is going to be 001, and the top of the content of the stack is xz0. One move is that, okay, using this transition, you can move to this configuration. You are still at Q0, you consumed 1, 0, so the remaining string is going to be 1, 1, and you pushed 1x, so the new content of the stack is going to be xxz0, so it's going to be something like this. This situation that you are at Q0 and you have read the first two zeros and the content of the stack is xxz0. Okay, so instead of actually just showing, I mean, one move, we can show you know, more than one move by putting a star over this transstyle notation. This is exactly, you know, we are going to find some kind of replacement for that delta star representation. Remember that we used for the finite state. This transstyle star is exactly representing that after a couple of steps, after a couple of moves, if from this configuration where I can reach. So after a couple of moves from this situation, after 2 moves you can reach to this situation. After 3 moves, for example, you can reach to this situation. After 4 moves you can reach to this situation. That this situation basically tells me that you have consumed the whole input string. There is nothing in the input string and there is nothing in the stack, and you are at a state Q2, which basically is the accepting situation for me, right? Because I have read the input string completely and I am in a final state, which is Q2. So now let's actually see a couple of more examples over the Pushdown Automata. We are going to create a Pushdown Automata for this language. The language is going to be the set of palindromes with even length. You can use, for example, binary strings. The sigma is going to be 0, 1. The set of all palindromes which has even length. For example, the 0, 0, 1, 1. 1, 1, 1, 1, something, all of these palindromes. So is it a context-free language? Yes, we can actually write a context-free grammar for this. If you wanted to actually, I mean, just as a reminder that how we can create a grammar for this language, this is going to be something like this. That S can goes to, if you are generating a 0 at the beginning, you should generate a corresponding 0 at the end of that as well. and each S can be replaced with one S1, that if you are generating a 1, at the beginning you should generate a corresponding one after that as well. Or it can actually goes to, for example, epsilon. Yeah, that's it. This is going to be the context-free grammar for this language. The length is going to be definitely even. You cannot create a, it's going to be palindrome, and it's going to be of even length, because whenever you generate a 0, you generate another 0, and whenever you're generating a 1, you generate another 1 as well. But I'm not going to discuss about, the context-free grammars and how they are equivalent to pushdown automata now. We will discuss it at the end of this lecture, but let's just stick to this fact that we are building a pushdown automata for this language. But before creating the pushdown automata for this language, I'm going to start with a simpler example, that we have a pushdown automata. We are going to create a pushdown automata for this string, that W is going to be any binary string. WR is the reverse of that, and basically this is going to be all palindrome binary strings that has a symbol, a unique symbol in the middle. This character C is not going to happen in the W or WR. Okay, so basically it tells me that where is the middle point of the palindrome. So all of the strings, like for example 0C0, 1C1, 01C10. Basically that C is going to be unique, and it tells me that where is the middle point of the palindrome. So the idea for creating a pushdown automata for this string is that I am going to, because whatever is the W, it should be, I should actually see it in a reverse order after reading actually C. So the idea is that before reading the C, all of the zeros and ones, basically the full string W, needs to be stored in the stack, so that after seeing, after you reach to C, you can actually start matching the remaining string with whatever you have in the stack. And a stack basically gives you this possibility that you read the string, and all of the tokens that you have read before, you can keep it in a reverse order in the stack, right? The last token that you have seen is going to be the first token on top of the stack. So if you have seen 001 C, so if you push the corresponding tokens on top of the stack, for example, X corresponding to 0 and 1 corresponding to 1, so it's just like you can actually, for each 0, you push 1 X to the stack, and for each one, for example, you push another token that shows that that's different than the 0, so a token like Y, and then you will reach to C. So basically this string that you have read, you have pushed it to the stack, and in the reverse order, the last token that has been pushed was Y corresponding to Y, which represent that this is going to be the top of the stack. This is the first token that you are going to have access. You can match it to the first token after C. Okay, this is the good thing about the stack. If you were going to actually see something like WCW, the stack is not going to help you to match a string like this, because you cannot have access to the bottom of the stack. You can only have access to the top of the stack, right? This is the property of the stack, that whatever you have read, the last item is going to be the first item that you are going to pop. This is a first in, first out data structure. So this is the whole idea. Before reading the C, for each 0, push one X to the stack, and for each one, push Y to the stack. And then after you see the 0, just move to another state, which is going to be a popping state. And then for each one that you will see, you should have a corresponding Y on top of the stack. And for each 0, you should have a corresponding X on top of the stack. That for each item, you will actually pop the corresponding, for each input token, you will pop the corresponding token from the stack. So using that idea, this is going to be the corresponding pushdown automata. I am actually using a specific notation here that, for example, remember I told you that at the beginning we are going to start at Q0, and for before seeing the token, the unique token C, you should push all of the zeros and ones to the stack. I mean the corresponding token to the stack, right? So it means that if you see a 1 and the top of the stack is 0, you push a Y to the stack. If you see a 1 and the top of the stack was Y, you just push another Y to the stack. You see that this token is the previous token. I don't want to pop anything from the stack. I just wanted to push another Y to the stack. Or if the top of the stack is X, you push a Y to the stack, right? Just because this number of transitions is going to be, there are a lot of transitions here. I found, one notation to make it shorter. I'm going to write it any here, and whenever you write any for the tokens, it just tells you that it doesn't matter what is the top of the stack, if it is Z0, if it is X, if it is Y, basically all the tokens that you can have all the symbols that you can have in the stack. This any basically means that the full, that G alphabet. Okay, all the tokens which are possible in the stack. It tells you that it doesn't matter what is the top of the stack. The action for me is that if you see an X, that just keep that token, don't pop it or just push it back, and push a Y on top of that. And similar to that for 0. If you see a 0 and the top of the stack, whatever is the top of the stack, just keep that token in the stack and push a Y to that as well. Okay, so it's just, the notation to, instead of writing 6 different transitions here, I can actually, summarize it using this notation any. I mean, there are different notations. I told you, if you search online and in different actually textbooks, people use different notations, but I think that would be understandable if you will get used to it. And after a couple of actually seeing different notation, you will understand that the meaning of each notation. So the first phase was that basically Q0 tells me that until you see that token C, always for each 0 push an X to the stack, and for each 1 push a Y to the stack. But whenever you see that token C, again, it doesn't matter what is the top of the stack, just move to the popping state, which is Q1. So you will see that it doesn't matter what is on top of the stack, keep it on top of the stack, and then move to Q1. In Q1, we start popping, but we should be careful. You can see that in Q1, I only have 2 transitions. If I see a 0, the top of the stack should be X. Then I can pop it. So if I am at Q1 and the top of the stack and the token is, the input token is 0, but the top of the stack is Y, there is no notation, and basically it tells me that the string is not palindrome and it's going to be rejected because there is no transition for that situation. In that situation, you don't have a transition and the machine will crash. It rejects the string. And for each one that you will see, the top of the stack should be Y, and you will actually pop it. Okay? And you only move to the accepting state if you have finished the input. You can actually move to the end of the stack in this, to the final state, even in the middle. But I mean, if you haven't actually finished the input string, but at Q2, there is no more action. So basically it tells you that you can only safely move to the final state if you have read the input strings completely and the top of the stack is also Z0, which means that everything before C has been matched. Everything before C, which was pushed to the stack, has been matched, and there is nothing in the input string and there is nothing in the stack. So this is going to be a string, a valid string in this form. So now we can modify the previous, this pushdown automata that we have created here, and create a pushdown automata for the original language which we were interested in, without that unique input symbol C. So I can modify this, right, and to create a pushdown automata for this language. The only action that I need to do is that basically there is no unique symbol C in the strings, right? So instead of having C, I can actually say that, okay, there is no input token for that, and I should replace this C with epsilon, which basically is going to give me a pushdown automata like this. This epsilon tells me that I'm moving from Q0 to Q1 without consuming any input string, which basically actually tells me that you can only move to Q1 safely when you have reached to the middle, to the middle of the string, and you have read the first half. Only in that way you can actually safely pop everything and you can move to Q2. But it doesn't actually tell me that. So it's actually just telling you that this is exactly the action that we have to guess when we are going to move. This epsilon move just tells me that I can move to Q1 at any time that I want, because it doesn't put any restriction over the top of the stack as well. It just tells you that anything can be on top of the stack. So basically this move tells me that I can move from Q0 to Q1 at any situation, right, without consuming anything from the input stack, which basically means that I have to guess when I have reached to the middle of the string. This basically reminds us as what would happen in the non-deterministic finite state, right? In the non-deterministic finite states, in some cases you could actually move to some situation and that action, that move was wrong. But if there is a correct move, if there is a correct set of transitions that end up to the accepting state, you were going to accept it in your finite state. This is exactly the same for the pushdown automata as well. If there is a sequence of the transition that end up to a final, to the accepting situation, we will accept the string. Here we can see, how the pushdown automata works over a string like this. This string is in our language. right? This is palindrome and the length is going to be even. I'm going to show you that how the pushdown automata will read this input string and will accept it. This is the starting configuration. You are at Q0. The input strings that needs to be read is 1, 1, 1, 1, the full string, and the top of the stack is Z0. At this situation, you can see that there are two transitions possible. Either you can use this transition here to just push one Y and stay at Q0, which is going to be this move, right? Moving to this situation. Or you can, this transition here allows you to move to Q1. You can see that it doesn't care what is the top of the stack. So even if the top of the stack is Z0, you can move to Q1 and just keep the top of the stack as Z0. So this is going to be that situation that moving to Q1, you don't touch the input string, you haven't read anything, and the top of the stack is Z0. You will see that this path is going to die because it's not going to accept the string in this path. But it doesn't really matter because I have another possible move here that I can follow. This path, again, in this configuration, in this situation, there are two possible moves. You can, again, use this transition to push another Y to the top of the stack and reach to this configuration, reading a 1, push another Y to the top of the stack and stay at Q0. Or you can, from this configuration, you can either go here or you can move to Q1, don't read anything and don't change, the top of the stack. Okay, again, this path is going to die because you can follow it. You can match 1, 1, and then after that, there is no more action. So this path is going to die. And basically, it is clear that why it dies, because you move to Q1 in a wrong situation. You haven't reached to the middle of the string, then you move to Q1. Again, in this configuration, in this situation, there is two actions. You can either stay at Q1 because this transition allows you to stay, right? The third symbol is 1. You can basically stay and just keep pushing to the stack, or you can move to Q1. You can see that here moving was correct. This action is going to actually end up to the accepting situation if you move to Q1, and this is the correct situation that you have to move to Q1. But you can actually also stay here as well. This exactly gives you the concept of non-determinism, that this pushdown automata is non-deterministic pushdown automata because at each situation you can have more than one possible transition, right? And if there is more than one possible transition, it shows non-determinism, but you will accept the string if there is one possible sequence of moves, one possible sequence of transition that end up to an accepting situation. This path here will actually end up, although all the other paths are going to reject the string, there is a path to accept the string and it will accept this string. So now we can actually move to the next topic, which discusses the deterministic versus non-deterministic pushdown automata. We have seen one example of non-deterministic pushdown automata. I'm going to show you a couple of deterministic and non-deterministic one. So just recall that what is the concept of non-determinism in the for our machine, for our automata. If at each position, if at each situation there is more than one possible transition for your string, whatever is the input string, if there is more than one possible transition, your machine is going to be non-deterministic. If always there is at most one possible action, one possible transition to follow, maybe there is 0. If there is 0 transition, it means that the machine is going to crash. So 0 is not going to make your machine non-deterministic. If you have more than one possible transition at any situation, your machine is going to be non-deterministic. Otherwise, your machine is deterministic. So now let's look at a couple of examples. This is the very first pushdown automata that we have seen, right? Is it a non-deterministic machine or deterministic one? If you think about the all set of transitions, you will see that there is no situation that based on the input, based on the state that you are in and the input string that you will read, it actually allows you to have more than one transition. So this machine is going to be deterministic because there is no possible situation that you have more than one move in your pushdown automata. So be careful. Unlike the finite state machines, that whenever you see epsilon in your transitions, you will say that this is going to be non-deterministic. Here, although I had that epsilon, I mean, don't consume anything from the input, but it doesn't make your machine non-deterministic. This machine is deterministic. Because the situation is that not only the epsilon actually matters, but also the top of the stack is going to be important for me, and this machine doesn't have any situation that based on what you are reading from the input and the top of the stack you have two possible moves. There is not possible. It's not possible. So let's see another example. Just think about this language. You can see that I just changed this situation that the previous, this is very similar to the previous language. I just changed the previous constant over k that was greater than 1 to k greater than 0. So if I'm going to create a pushdown automata for this, I can just, whatever the pushdown automata here that I had, I can modify that. You can see that here I only move from Q0 to Q1 only if I see a 1, right? It doesn't actually allow me. It basically means that you should have at least 1 0, and then based on that you should have at least 1 1. Then you can move from Q0 to Q1. So I can just modify this pushdown automata to create a pushdown automata with this restriction that also allows epsilon in our language. So I wanted to have epsilon in the language. The only difference between this language and the previous one is that epsilon belongs to this language, but it doesn't belong to the the previous one. So basically the only thing that I have changed was this transition. That basically this transition means two transitions. You can move from Q0 to Q1 either if you have X on top of the stack. So basically it's not going to pop it, just keep it, because we are going to match all of the zeros and zeros and ones, right? So it's actually telling you that you can move to Q1 even if you haven't actually read any one, right? So if this is X or if this is Y, the top of the stack, don't touch it. Go to the popping situation, and I'm going to pop all of the X's here. So now you can actually see that this just changing this transition, the previous transition to this two transition here, is going to inherently actually, completely change the pushdown automata. Is this pushdown automata deterministic? The previous one was deterministic. This pushdown automata was deterministic, but is this one also deterministic? if you think about it, you will see that this pushdown automata is not deterministic, and basically because of these two transition here. That tells me that if you are at Q0 and the top of the, what you actually read is 0, for example, something like, for example, a string like 0, 1, what would happen? You are at Q0 and the content that you have in the string, the input string is 0, 1, right? And the top of the stack is Z0. In this situation, you have two possible moves. You can either, using this move here, you can either go to Q1 without actually changing without reading anything from the input. Go to Q1. Or you can actually read that 0, stay in Q0, read the 0 and push an X2, right? So in this, at the beginning, I had actually two moves, two possible moves. And that's it to make it a non-deterministic pushdown automata. This machine is not deterministic anymore. How about this pushdown automata? Remember we created this pushdown automata for the palindrome strings that has a unique symbol C in between. Is it a pushdown automata? Is it a non-deterministic or deterministic pushdown automata? This list here shows you all of the transition and basically helps you to determine that if there is any situation that I can have more than one move, and no, there is no such a situation in this case. Everything is very deterministic. Before reading a C, you will always actually have to push your actual things in. You will stay at Q0 and you will push, and whenever you see a 0, you have to move. There is no other action here. You have to move to Q1, and in Q1 you have to pop here. And at the end, whenever you reach to Z0, the top of the stack should be Z0. Only in that case you can actually move to Q2. And yes, this is going to be a deterministic pushdown automata. So you can see that this action is, this move is not going to be possible if you have you still have anything in the stack. So basically you can only reach to this action only you have read completely, you have removed everything from the stack. That's why it actually makes it a deterministic pushdown automata. How about this one? Remember we have actually changed the pushdown automata by adding actually a couple of moves here that allows you to move from Q0 to Q1 at any situation. We have already actually discussed about that. Yes, this is non-deterministic because this set of moves here is going to allow you to move from Q0 to Q1 at any position, basically because you don't know when you have reached to the middle state, you have reached to the middle of your string. So this set of transitions here that we have written, this set of transition, I mean all of them are going to be representing using this one, right? All of these three transition basically makes your machine non-deterministic and allows you to move from Q0 to Q1 at any situation. And this is going to be non-deterministic. So, but why we are talking about deterministic and non-deterministic machines? For non-deterministic pushdown automata, unlike the regular languages that the deterministic and non-deterministic finite states had the same power. So if you have a NFA, any NFA could be converted to a DFA, right? It was possible for the regular languages, and basically DFA and NFAs are going to be equivalent. If you have a DFA, basically a DFA is going to be an NFA, and every NFA could be converted to a DFA. But this is not the case for the context-free languages. We can say that all those languages that can be represented using a deterministic pushdown automata is going to be a set of the languages that can be represented using a non-deterministic pushdown automata. So basically, non-deterministic pushdown automata has a more expressive power than deterministic pushdown automata. And we can say that these languages that we have here, they are going to be context-free. They are not regular, right? But they are simpler. They are a subset of the full set of context-free languages. And that's why we call actually this set to be deterministic. CFL. Sometimes we call it actually deterministic context-free languages. And they are going to be a subset of context-free languages, the full set of context-free languages. And basically they are telling us that the machine that is required to represent these languages are going to be simpler and more efficient than the non-deterministic one. Basically the reason is that in the non-deterministic pushdown automata you have to consider a lot of different paths, right? But in deterministic one, only one path is going to be actually enough, and the language is going to be simpler, more efficient to represent, more efficient to accept. So let me actually show you a couple of examples of the languages which are deterministic, and those which are non-deterministic context-free languages. I mean, if I wanted to actually go back with the example, this example that we have seen, the language of palindromes with even length, okay, this language is inherently non-deterministic. You cannot create a deterministic finite deterministic pushdown automata for this language. And the reason is that exactly we never know that when we have read the half of the string, the first half of the string. That's why we have to actually keep these non-deterministic moves that allows us to move whenever, at every possible situation. Unlike this language, that by putting that C in the middle, you make it much simpler to actually recognize, because you always know that when you have reached to the when you have read the first half of the string, when you have read W, because of this symbol. But because we don't have it in this language cannot be represented using a deterministic pushdown automata. This language, the language of palindromes with even length, is going to be non-deterministic context-free language. So let's see a couple of more examples. For example, the set of all palindromes with odd length. The previous one with the palindromes with even length, this one is a palindrome with odd length. Something like, for example, 0, 1, 0, 0, 0, 0, right? So is it a deterministic context-free language or a non-deterministic context-free? Can we create a deterministic pushdown automata for this one or not? If you think about it for, sometime, you will see that the issue that we had with the palindromes with even length, we exactly have it here as well. We never know that, although the length is odd, again, we never know that when we have reached to that middle character, right? And because we never know, the moves that we need to actually allow is going to make our machine non-deterministic. And so this language is going to be a non-deterministic context-free language, and the only pushdown automata that we can create for that is going to be non-deterministic. And now we can actually see that if you make you talk about the language of all palindromes, binary palindrome strings with even or odd length. Basically, this is the union of the previous two, and this is going to be non-deterministic as well. You would, I mean, the argument is the same. You never know that you have reached to the middle, whenever you have reached to the half of the string, to the middle character, or you have read the half of the string. And the pushdown automata for that is going to be represented like this. And you can see that here I have also actually put any here. Be careful when I'm actually putting any at the, for the input character, it basically tells me that it can be anything from the alphabet, and also it can be epsilon. Okay, but when you are talking about any over the over the stack token, it will be only a token from the alphabet of the stack. Any, in this case, cannot be epsilon. Basically, in each move, you are reading something from the top of the stack. You are removing something from the top of the stack. So if I'm using any for the input string, it covers epsilon as well. But for any for the stack, the symbol is not going to cover the epsilon. The reason is that you always actually needs to pop something from the stack. Okay, how about this string, this language? Is it a deterministic or a non-deterministic context-free language? It is context-free language. We have actually created a context-free grammar for it in the previous lecture, so we know that this is context-free. But is it a context-free? Is it a deterministic context-free language or a non-deterministic? Can we create a deterministic pushdown automata for that? So we can create a pushdown automata like this for the language. You will see that the idea here is that, okay, whenever I see, this is going to be the set of strings which are, you can think of it as, for example, 0 is open parentheses and 1 is close parentheses. So 0, 1 is going to be balanced. 0, 0, 1, 1 is going to be balanced. Right? 0, 1, 0, 1 is going to be balanced, just like a, this open, close, open, close. These are the balanced actually strings. And the whole idea is that, okay, for each 0, which is corresponding to an opening parenthesis, you will push something to the stack. And for each one, you have to pop a corresponding actually 0 from the top of the stack. I mean, I can actually represent it as for example, a token L. That for each 0, I will push 1 to the stack, and for each 1 that I will see, I will pop it from the stack. This pushdown automata is going to accept this language. But is this pushdown automata deterministic? You can see that no, this pushdown automata is not deterministic. Again, because this transition allows you that, for example, if you have a string like 0, 1, at the very beginning, you are at Q0, right? So let me actually show it to you in a more formal way. Okay, just think about this simple example that your string is 0, 1. At the very beginning, you are at Q0. The top of a stack is Z0. Okay, so you can either push an L to the stack, right, and go to this situation that you stay at Q0, you read the 1, 0, and you remain with 1, 1, and you have L on top of the stack and Z0 as well in the stack. Or using this transition, you can actually move to Q1. That Q1 you haven't read, anything, and the top of the stack is Z0, right? Definitely this is going to actually end up to actually die, right? Because there is no action at Q1 for this situation. This is going to be the correct move. But anyway, this makes your pushdown automata a non-deterministic one. So this is a non-deterministic pushdown automata. But does this mean that this language cannot be represented using a deterministic pushdown automata? No, I can create a deterministic pushdown automata for this language. This is a deterministic pushdown automata. You can see that it can actually capture any balanced string, even actually epsilon. Epsilon is a balanced string, right? In terms of, I mean, the parenthesis concept. Epsilon is balanced and it will be actually accepted. It started at Q0, which is an accepting state. Whenever you started actually seeing some input string, you will move to Q1 and you will stay there, match all of the zeros and ones, and you only actually go back to actually Q0 if you have read and you have matched all of the zeros and ones. So this pushdown automata is deterministic, and yes, this language is going to be a deterministic context-free language. We can create a deterministic pushdown automata for that. The very first example that we have seen among the non-deterministic ones, remember this pushdown automata for the language of the number of zeros and k's, that the number of k number of zeros followed by k number of ones, which also actually covers 0. This pushdown automata that we created for that was non-deterministic. But does this mean that the language is inherently non-deterministic context-free language? Can't we create a deterministic language for deterministic pushdown automata for this? The answer is no. This language is a deterministic context-free language. I can create a deterministic pushdown automata for that, and this is going to be the deterministic pushdown automata for this language. And you can see that it actually accept epsilon and all the other actually strings of length greater than 0 as well. But why we care about the deterministic and non-deterministic pushdown automata? Basically, because deterministic pushdown automatas are going to represent more efficient machines. I mean, you can run them much more efficiently than the non-deterministic machines. And the languages that can be represented using a deterministic pushdown automata, they are going to be simpler than the languages those context-free languages that cannot be represented using a non-deterministic, using a deterministic pushdown automata. And one more important thing about the deterministic pushdown automata is that all of the languages which are deterministic context-free languages, that they can be represented using a pushdown automata, you can create a non-ambiguous grammar for them. Okay? But this is not an if and only if statement, because there are some grammars, there are some languages that we can create an ambiguous grammar for them, but we cannot create a deterministic pushdown automata for them. So this statement is not a if and only if statement. And if I'm going to actually just summarize it, the regular languages, all of them are going to be a subset of deterministic context-free languages, and they are going to be a subset of the full context-free languages which can be represented using a non-deterministic pushdown automata.